Hi folks! In today's video, we will do a walkthrough of a project that utilizes our Arduino programming skills in an Internet of Things app called Blynk to make an automated hydroponic garden so we can grow our own tasty food. Why, you may ask? Well, first, because hydroponics is super cool, and through this project, we will demonstrate many potential uses of the Arduino. Hopefully, with this walkthrough, we'll give you some skills, but more importantly, some inspiration to create dozens of other cool IoT projects powered by Arduino. But hold on, what the heck is an Arduino? A sub sandwich? And who is this IoT lady? If you're asking yourself these questions, have no fear. We have some great videos on our YouTube channel that introduce exactly what an Arduino is and its many uses, and we'll provide those links below. We've also included timestamps for this video since it's on the long side, in case you want to jump to a specific section. If you're unfamiliar with the term Internet of Things or IoT, we also have a great mini course for our members at Programming Electronics Academy that teaches all the essentials to get your projects up and running and connected to the cloud. And this is just the tip of the iceberg. We've got 8 courses and counting, which cover everything from electronics fundamentals all the way to using LCDs and servos in your projects. If this is your first dip into the world of making and prototyping, welcome aboard. You're in the right place to start your Arduino adventures. So, what is hydroponics anyway? Hydroponics is a method of growing plants without soil by using a water-based nutrient solution instead. There are many different types of hydroponics, and they vary in how the nutrient solution is distributed to the plants, as well as how the nutrients are mixed into the water. Take aeroponics, for example. That's a method of misting the plant roots with fine drops of the nutrient solution, usually on a timed schedule. For our project, we're going to create a drip system that is similar to the popular tower garden setup. If you're looking for an excellent product that requires no building on your own, definitely check out towergarden.com. Hold on, what about aquaponics? Isn't that the same thing as hydroponics? Well, not exactly. Aquaponics is the method of combining aquaculture, like raising aquatic animals such as fish, and hydroponics. Essentially, you use the fish poop to add the required nutrients to your water solution, and then you distribute the water to the plants. Why should you build this project? Well, like we said before, we hope it will show you how cool Arduino is and give you the inspiration and confidence to build other microcontroller projects. But more than just that, growing your own food is fun and easy. Adding the Arduino to the traditional hydroponic setup helps automate the process so even the most unskilled gardeners can find success. It also tastes great, and you know exactly what's going into your plants. Hydroponic gardens don't require weeding, and there's no messy soil involved. And it allows you to grow vertically, taking up less space, so even people in small apartments or those who don't have backyards of their own can grow. It allows you to grow your favorite produce anywhere at any time of the year. I even grew these vegetables in England in the middle of winter, during weeks of freezing temperatures and no sun. And lastly, it uses up to 90% less water than traditional growing methods. Although your power bill may be higher, so we're definitely not arguing it's more green than using soil. That's for someone else to discuss. Before we jump in, just a quick disclaimer. We normally go much more in depth when it comes to walkthroughs and lessons, but we were so excited about this video, we wanted to get the content out relatively quickly. If you'd like to see a full-blown PEA-style course on how we made this, similar to our IoT barbecue Wi-Fi thermometer course, please let us know in the comments, and if there's enough interest, we'll go ahead and develop a multi-part series that will dig much deeper into the construction and the code analysis for this project. Another thing to note, we used a 3D printer to create our system, but you can definitely create a similar system from common materials available at your local hardware store. Check out this really excellent walkthrough from the Over 60 Crafter. We think this is one of the best DIY hydroponics available on YouTube. See below for a link to her video. And if you have a 3D printer, or maybe a friend that has one, or perhaps want to use a 3D printing service available online, you can access our STL files for free at programmingelectronics.com. See below for a direct link. So, how did this project get started anyway? Well, we won't mention any names, but someone who happens to be the spouse of one of our PEA staff members has tried many times to start a garden at home. While the attempts have been valiant, each and every time the garden resulted in a bed of death. This was usually caused by the spouse becoming very busy due to work commitments, and the plants would unfortunately be neglected and not watered regularly. We're not talking one bed of death. We're talking many, many gardens of despair. So, the spouse teamed up with the husband to come up with a solution where the watering is automated and could be monitored from afar. Thus was born the idea for the Programming Electronics Academy Garden, or the P Garden. Well, it's a working title. If you can think of something more witty, please let us know in the comments. To recap, the project has to be automated, i.e., self watering, and monitored from afar, i.e., the nutrient level in the reservoir has to be monitored via the internet in case the system starts running low on nutrients. The initial iteration was left next to a window for 2 weeks, and the side that was away from the direct sunlight ended up dying, and the side closest to the window thrived. So the second iteration incorporates rotation, thus ensuring all the plants receive equal amounts of sunlight. Let's review the various components of the system. See below for a link to the bill of materials, which will provide links to all the components. At the very bottom, you can see we have a reservoir, which holds about 2 gallons of nutrient solution. We bought this one from IKEA for around 20 bucks, but a regular old bucket would work just as well. Next, you can see how the system interfaces with the reservoir. We'll call this red part the base adapter. Here you can see there's a small gap between it and the part sitting above it. This gap needs to be there just right so that the top piece can rotate freely. Someday we'll add some ball bearings here, but for right now, this seems to do the job. While we're looking at the base adapter, you can see the water level sensor. We got this from an online electronics retailer called Adafruit.com. The product is called a 12-inch standard E-tape liquid level sensor. This allows us to measure how much nutrient solution is left within the reservoir. Also, here you can see the water pump, the 3 servos, 3 gears allowing the servos to couple to the main system, and a flexible pipe that connects the pump to the rest of the system. A quick note on the servos. Yes, the easiest solution and least complicated is adding some grow lights that surround the garden. We were trying to avoid this option so we could reduce the electrical bill and harness the power of the sun. In the end, we ended up buying 2 grow lights as the sunlight available in the UK winter was just not sufficient. The rotation does make it snazzier, so if you live in a region that has plenty of gorgeous sunshine, this solution may work just fine for you. Also, 3 servos may seem a little overkill, but we found that this worked best versus 1 extra powerful servo. Mileage may vary for your garden, however. Next is the large extended spur gear. This is the first of the large pieces that rotate, and the large gear is what interfaces with the 3 smaller gears attached to the servos. Notice that the top of the part is threaded. This is how it connects to all the parts above it. This makes it modular as well, so you can add or subtract as many levels as you want. Next is the threaded module. Add as many levels as you'd like. Each module contains 6 spots for 2-inch net cups. From this view, we can also see the stationary pipe that's in the center. The pipe, the base adapter, and the distributor at the top of the pipe do not rotate. The modules and top reservoir rotate around the stationary pipe. That leads us to the top reservoir. The purpose of this is to collect the nutrient solution and allows for even distribution on all sides of the system via these small holes. It has a top lid and a handle to make it easier to transport. Last but certainly not least is the brains of our operation. Here you'll see our enclosure with a power supply going in on one end, and the other end are the wires that power and control the servos, the water pump, and the water level sensor. Inside the enclosure, we have the microcontroller. We went with the ESP8266 Node MCU due to its low cost and ease of use. You could just as easily use another board that's compatible with the Arduino IDE. The power supply takes 100 to 240 volts AC power from the wall, or 230 in our case, and converts it to 12 volts DC. The water pump operates at 12 volts, and we have a relay that allows our microcontroller to signal it on and off. We also have a buck converter that steps down the voltage from 12 volts to 5 volts to power the microcontrollers and the servos. Here you'll see a simple on-off switch, allowing us to control power to the system. Lastly, you'll notice that we've got a beefy terminal block in the enclosure. Since the pump will be drawing a substantial amount of current, we want to make sure that the electrical connections and wires that we are using can handle it. That's all of the components for the PEA garden. We won't cover the materials you'll need to actually grow the plants, like the seeds, nutrients, net cups, etc. But as a reminder, if you head over to the PEA website, you'll find our bill of materials, which has all the relevant parts, and links to where you can buy them, as well as links to all the plant stuff you may need to start growing. If you're savvy with hydroponics, you might be wondering why we didn't include a parts per million sensor or a pH sensor. While admittedly it would be cool to monitor this remotely, we discovered that they were just not necessary for our final project. As long as you check the ppm and the pH when you make a new batch of solution, the pH and ppm doesn't normally drift enough to make a difference in between solution swap outs. At first, we were swapping solution every 7 days, but as our plants got bigger and thirstier, we were having to swap it out every 4 to 5 days or so. The wiring of the brain is a bit complex, simply due to the number of total wires in the project, but generally it follows this schematic. Now, this is the final solution, and we're going to break it down bit by bit. But first, we'll write a high-level algorithm that goes over the main functions that we want our project to accomplish. Our 4 main objectives are 1. Turning the water pump on and off for a specified amount of time. 2. Periodically rotating the garden 1/6 of a rotation. 3. Sending the water level to our app. And 4. Making some settings adjustable from our app, such as the pump running time. Seems pretty easy when we lay it out like that, and to be honest, from a coding perspective, it is a pretty straightforward problem if you know how to program the Arduino. Likely, the hardest part of this project will simply be constructing the apparatus in the first place. We're going to start tackling this algorithm by using the lowest hanging fruit mentality. That is, we're going to solve the easiest problem first and try to build some momentum in our project creation process. The easiest thing here will be turning the pump on, allowing it to run for a set amount of time, and then turning it off, letting it rest for a set amount of time, and then repeating the cycle. Next, we'll get the servos operating and the garden rotating. After that, we'll get the water level data sent to our app. This will involve connecting our microcontroller to the Wi-Fi, reading our sensor, and then sending that data to our app. And lastly, we'll combine all 3 and make it so you can adjust some of the settings via the app. So if you want, you can make small tweaks and you won't have to upload new code every time. So let's take a crack at function 1, turning the pump on. We will do this using a relay. If you're not familiar with relays, they basically are an electromagnetic switch that is operated by a relatively small electric current that turns off or on a much larger electric current. So we need to send a small amount of current to our relay, at which point it will activate and close the circuit between our pump and the power supply, and the pump will then turn on. We can do this via the digital write command from our microcontroller. We tell the ESP8266 to make a pin high. The relay then closes the switch and our pump turns on. We wait a predetermined amount of time and then make the same pin low. The switch opens again and our pump turns off. Easy. One method that's very helpful when prototyping is to build the experimental circuit in Tinkercad. There you can see if it works, and if so, then you can build it in the real world. If you're unfamiliar with Tinkercad, we have a great video detailing the features of it, and the link is down below. So let's take a look at the circuit we've created in Tinkercad. Our power supply takes 220 VAC, or volts AC power, from the wall and then converts it into 12 volts DC, up to 6 amps, which is represented by our power supply here. From there, we connect to our terminal block. You can see that we've got the 12 volts power bus represented by the red wired breadboard here. The ground bus is represented by the lower half of both these breadboards and is wired so that anything connected here will be in parallel. Finally, this LM7805 5-volt regulator here represents our buck converter, and as you can see, it has 12 volts coming in and 5 volts going out, which is connected to the 5-volt power bus. Generally speaking, the 12V bus will power the pump, and the 5V will power everything else, including the ESP8266. For the purposes of testing our circuit, we'll use an Arduino UNO because Tinkercad doesn't have an ESP8266 available. It should work the same, but we just need to keep in mind that the ESP board uses 3.3V logic and the UNO uses 5V. The motor represents our pump, and when it's running, we can assume our pump would be running instead. Finally, we have our relay. You can see the high voltage circuit here, and the red 12V wire from the 12V bus goes into the circuit, then comes back out and goes into the motor. This is the circuit that's open or not active. When we write digital pin 2 high, this sends 3.3V, because it's an ESP8266 in real life and not an UNO, to the relay, which energizes the magnetic coil. This closes the relay switch and then the pump turns on. When pin 2 goes low, the switch opens and the pump stops. Essentially, what we're doing in this sketch is no different than the first program most coders learn when they learn to code, which is just blinking an LED on and off. Now, if you've never coded anything in your life, this may look and sound pretty foreign, but I assure you, with just a little background knowledge, you can learn this relatively quickly. Do yourself a favor and take our Arduino course for absolute beginners, and the code in this project will seem like child's play. Even if you're unfamiliar with coding, stick with us. You'll be able to understand the broad strokes of what we're doing, and it might persuade you to start learning. All right, pep talk over. Now let's go line by line through our code. First, we start by declaring two variables, our pump on time and pump off time. We've gone with 15 minutes for both, so to convert that to milliseconds, we need to multiply 15 times 60, then times 1,000. But feel free to modify these times, that's just what we've found works best for our plants. For our Tinkercad experiment, however, we'll reduce this just to a few seconds so we can test it out and not have to wait 15 minutes. Next, per our wiring diagram, we declare relay pin as 2. In setup, we'll make that pin mode an output. In the loop, we turn on the pump, delay, let it run for our pump on time variable duration, then we turn it off. We then let it rest or not run for the duration of our pump off time variable. So we verify the code and it checks out. Then we copy and paste it into Tinkercad, change the variables to 2000 milliseconds or 2 seconds, and start the simulation. Voila, it works as expected. Here you can see a video of our very first iteration of our hydro garden. This is the first time we turned it on using the code we just wrote. Okay, next we're going to get the garden rotating. Again, back to Tinkercad so we can set up our experimental circuit. We'll keep the relay and pump around, but let's delete all these wires so that things look a little less cluttered. In the actual project, our servos are the continuous rotation type, which allows them to spin continuously, either clockwise or counterclockwise. This is different from the standard servos that are usually limited to a 90 or 180 degree of movement. In Tinkercad, they actually don't have the 360 degree servos, so we'll use the standard ones that they offer, but just realize the positions they go in are not what it will look like in real life. To move servos with an Arduino compatible board, we use the built-in servo library. The right function of the servo library is what we'll use for rotation. For continuous servos, instead of telling them what position to go to, you tell them what speed and direction to rotate in. When 90 is written, the servo speed equals 0. When 0 is written, the servo speed rotates at maximum speed in the counterclockwise direction. When 180 is written, the servo rotates at maximum speed in a clockwise direction. So for our purposes, we'll write 120, which equates to about 1/3 max speed in a clockwise direction, and we'll rotate this for about 3 seconds, which roughly equates to 1/6 total rotation for the garden. This means every 6 full cycles, the garden will have rotated 360 degrees. If any of this is unfamiliar to you, we have an excellent servo course at programmingelectronics.com that will teach you the fundamentals of using servos with Arduino. With everything wired correctly, let's jump into our code. So first, we include the servo library. Next, we create the instances of the servo class called myServoA, myServoB, and myServoC. We declare a few variables. First, we define the speed like we talked about before, and we also define the rotation time. Again, these two can be tweaked to get the right amount of rotation. We recommend turning the garden a fraction of the total number of openings you have per module. We have 6, so we're going to turn it 1/6 of a full rotation, or about 60 degrees. Next, we'll define the pins where the servo signal wires are attached. In setup, we'll attach each of the servo instances to a pin. Down in the loop, we'll start off writing a servo speed to each of the servos. Then we delay for the defined rotation time. Lastly, we turn the servos off by writing 90. We added a delay of 5 seconds so you can appreciate the end of a cycle. Okay, let's copy the code, put it into Tinkercad, and hit Start Simulation. Looks like it works. All right, it's time to test it in the real world. Here is a video of a test we ran with 20 pounds of weight on top of the garden to simulate the massive plants we would be growing in the near future. We simulated it running for 3 months by reducing the duty cycle and ran it overnight. Thankfully, even under load, it held up. Okay, we're making some serious progress here. Next, let's see if we can get the water level sensor working. Our E-tape liquid level sensor has one pin for power, either 3 volts or 5 volts will work, one pin for ground, and on the third pin, we can measure voltage and relate it to the amount of liquid remaining in our reservoir. It's got a pre-built voltage divider on board, so we know the output voltage we'll be measuring will be somewhere between 0 and 1 volts. We also know that this voltage varies linearly with the amount of water it's measuring, so to keep things very simple, we'll measure the voltage when the reservoir is full, and we'll take another measurement when the reservoir is just about empty, when the water level is just above the top of the water pump. We'll call these two variables low E-tape value and high E-tape value. Then we'll use the map function to calibrate an output that makes sense. If you're getting a little lost here, check out our IoT course for more information regarding voltage dividers, and our Arduino Basics course to find out more about the map function, both which are available at programmingelectronics.com. So let's see what we can build at Tinkercad for this one. While our E-tape is not available as a part, we can still use a temperature sensor that they offer as a substitute to check our code and our wiring. As you can see, you can adjust the temperature the sensor is exposed to, which changes the voltage that's sent to the microcontroller. So this will replicate our E-tape quite nicely. Let's take a look at the code. So after quite a bit of trial and error, I can tell you that those readings for low E-tape value and high E-tape value are accurate for the reservoir which we chose. But you'll need to do some experimentation to determine the correct values for your system. You'll see how this is done once we jump over to Tinkercad. So let's copy and paste this code and see what happens. As you can see, after we open the serial monitor, the raw data and the liquid level are printed. As we adjust the temperature at the sensor, these values go up and down. But the liquid level is showing some negative values. This is because the E-tape values are set for the actual project. So let's see what happens when the temperature is at its minimum. Looks like the value is 20. Now what about when it's at the maximum? Looks like it goes up to 358. So let's pop these values into the code and see what happens. Now you can see when we slide the temperature all the way down to the minimum, the liquid level shows as 0%. And when we slide to the maximum, it shows 100%. Nice work. This is the exact technique you'll use to apply this to your own project in order to calibrate the liquid level. The next part of this walkthrough is going to assume a bit of knowledge. First, that you're familiar with the Blynk app. If you're not, check out our barbecue thermometer class. It goes super in-depth into Blynk. You can find this course at programmingelectronics.com. The second thing we'll assume is that you're familiar with the millis function. The millis function allows us to get rid of any delays in our code, which would essentially jam up the connection between our device and the Blynk app. We want tight loops, otherwise Blynk fails. If you're unfamiliar with millis, check out our free millis mini course, and you'll see below, the link is in the details. Now, using the same wiring for the E-tape, let's revise the code. So the goal here is to take what we already have to find the liquid level and add some IoT functionality to it by injecting some Blynk code. First, we include the required Blynk libraries, and then we also supply the unique authentication token which we'll get from the Blynk app. We also provide the Wi-Fi network name as well as the password so our device can connect. Previous time we'll set to 0, and sample time, well, this is how often we want to push the data from our E-tape sensor to our app. Let's start with every 2 seconds. The next new bit of code will be in setup, where we add blynk.begin. This function instructs our device to connect to the Blynk servers with our credentials. We put it in setup because we only need to connect once. Next in the loop, you'll see that instead of using delay sample time, we're going to instead utilize the millis function. This allows us to keep running through the loop. A delay would stop everything, and therefore our connection to the Blynk server would be severed. We set current time to millis, which means current time will always correspond to the internal stopwatch within the ESP8266 board. It starts at 0 and goes for approximately 50 days, and then starts back over at 0. So this is something to keep in mind if you're ever going to leave your garden for more than 50 days. Next is the blynk.run function, which is required to maintain our connection to the Blynk servers. Next, you'll see an if statement. If current time, let's say 1000 milliseconds, minus previous time, which right now is 0, is greater than or equal to sample time, then it will run the code below. If not, it will skip down to the next bit of code. Well, in this case, 1000 minus 0 is 1000, and that doesn't exceed 2000, which is what we've set as our sample time. Therefore, we'll skip this if statement. But there's nothing else in the loop, so we'll just start right back at the top of the loop again and we hit blink.run, which is perfect. That's what we want to maintain connection. If we delayed, it would be 2 seconds before blink.run would be executed and we'd have some major problems. What happens when millis equals 2000? Well, 2000 minus 0 equals 2000, so our if statement is true. This means we'll execute the code. All of this should look familiar from when we initially set up the sensor. At the end, you'll see 3 new lines. Blink.virtualWrite, V1, raw liquid reading, then blink.virtualWrite liquid level, and finally previous time equal current time. When we execute virtual.write, we're pushing data to the virtual pin. On our Blynk app, we'll add widgets, which are set up to receive this data. We've designated virtual pin V1 and V0, so when we make our app, we'll need to remember to assign our displays to these pins. Lastly, we have previous time equal current time. So after the first time through, previous time will now equal 2000. When we execute the loop again and arrive at the if statement this time, current time we'll say is 2500, and we subtract previous time, which is currently 2000. We get 500. Is 500 greater than or equal to our sample time of 2000? No, it's not. So we continue running through the loop. We've got 2 more bits of code at the bottom, which aren't really necessary, but I added them to help me do some troubleshooting. We've got a function called blink_write for virtual pin 2. When we change the value of V2 on the app, this data will be pushed to whatever we designate inside this function. So on our app, if we change the value of V2, it will be pushed to the device, assigned to sample time, and converted to milliseconds. This allows us to adjust the sample time or refresh rate on the fly. Last, we've got Blynk connected. This is executed only once, when the device first connects to the Blynk app. Blink.syncVirtual ensures that before the code is executed, we sync our pins. Therefore, if we had V2 equal to 4 and the device connects, sample time would be assigned to 4000 instead of the default 2000, which we declared at the beginning of the sketch. Before we test it out, let's take a quick look at our Blynk app. First, we have a super chart widget. You can put all kinds of data streams into this guy, but for our purposes, we're going to just display the liquid level percentage, which is virtual pin 0. Next, we have the value display widget for our raw liquid reading. This really isn't necessary, but it's nice to see what value is actually being read at A0. This will correspond to virtual pin 1. Next, we've got another value display widget, this time liquid level. This should match exactly what's on the chart, but again, nice to see data read out instead of just in a line on a chart. Last but not least, we have a step widget. This allows us to adjust the sample time or refresh rate. You can adjust the step if you want to increase or decrease how much the value changes every time you hit the up or down button. We'll leave this at 1 for now, and this corresponds to virtual pin 2. So that's about it for the app. Let's see this thing in action. Okay, we're just about there. The last thing we need to do is combine all these sections into one big sketch and make sure they're all compatible with the Blynk app. Remember that delay functions won't work with Blynk, so that means we need to edit both the pump on and off as well as the servo code. We'll check out the new edits in the code, then we'll check out the Blynk app. And finally, we'll show this baby in all her glory. So the big picture strategy for the code, we know we have to get rid of the delays. In order to do this, we're going to break everything down into states, or for clarity, we'll call them phases. The first phase is that we'll rotate the garden. The second phase will turn the pump on and then shut it off. And third, we'll let the pump rest, and at the same time, we'll take a measurement of the liquid level. That equals 1 full duty cycle. Then we'll do it all over again. Let's dig into the new lines of code that we haven't seen yet. First up is where we declare the string variable pump state. This will be used later. Everything else all the way to the loop we've seen before, just never all together in one sketch. The next new line is static byte state equals 1. This is to make sure the sketch starts where we expect it to at our state 1 code. We put static in there, which means it will only be executed the first time through the code. The next time through, this line will be ignored. So let's jump into state 1. The first part, the if statement, is checking to see if we've exceeded rotation time, and if not, we'll jump down to the else if statement. This is checking if we're in state 1, which we are, and if the servos are attached. If not, then we'll run the user function servo attach then rotate. This is a mini function which we created to attach all the servos and write them to the servo speed variable, which we previously defined. We don't want to constantly write the servos, we just want to set the speed once and then let them run. That's why in the else if statement, we're checking if they're attached or not. So the second time through the loop, they are attached, and thus the else if statement is skipped, and we're just continuously running through the code until the if statement is satisfied. Once rotation time has been reached, we'll execute the code in the if statement. We'll run the servo stop then detach user function, which surprisingly does exactly what the name says, and we'll change the state to 2. We'll then set previous time to current time, and as you can see, state 1 is accomplished and on to state 2. So now the same deal with state 2. We first check to make sure we're still in state 2, i.e. pump on time has not yet been exceeded. If not, let's jump down to else if. Similar to the servos, we're checking to see if the pump is already on by checking the variable pump state. Remember, we've declared this before as off and we're in state 2, so we can execute the code in the else if statement. We'll write our relay pin to high, which activates our relay and then turns the pump on. We'll also change our pump state to on. The next time through the loop, because the pump is already on, we'll skip this else if statement and keep running through the loop until pump on time is reached. At this point, we'll write the relay pin low, which will turn off the pump. We'll change the variable pump state to off for the next time we get to state 2, and as normal, we'll change state to 3 and previous time to current time. Okay, on to state 3. Finally, for state 3, this is really just our code from the last sketch. We'll check if pump off time has been reached, and if not, the pump stays off and the loop runs. Once it's reached, we'll check the liquid level, push it out to our Blynk app, and then set the state back to 1. And the circle of life begins all over again. And that's it. Everything after the end of our loop is the custom functions. One thing to note, we did add some additional Blynk write functions so you can fine-tune your project from the app. You can adjust servo speed, rotation time, pump on time, and pump off time. This is useful so you don't have to re-upload any code to your device. You can just use the app to adjust these parameters. We made it! We really hope you enjoyed this video and that you have great success building your very own hydroponic garden. As a reminder, you can find all the code, STL files, and much, much more at programmingelectronics.com. And listen, if you made it this far and you're still wondering if this Arduino stuff is too tough to learn, I can assure you it's definitely attainable. You'll be amazed at what you can do with just a little Arduino coding knowledge. And if you want to jumpstart, check out the training program at programmingelectronics.com.